I still remember when the internet felt like actual magic, just instant communication anywhere. But it feels like we're on the verge of the next big leap, the quantum internet.
We absolutely are. And this isn't just about making things faster.
No, it's about security, right?
Exactly. It's about fundamentally secure communication. The problem is our current security, things like RSA encryption that protect, everything online, it's all based on math problems that are hard to solve.
Hard, but not impossible, especially for a quantum computer.
Right. A large-scale quantum computer running Shor's algorithm could basically crack them. It makes our current systems very vulnerable.
So that's why we need quantum key distribution, QKD, because its security isn't based on a math puzzle. It's baked into the laws of physics.
Precisely. Unconditional security. But that brings us to the real challenge, the mission for this deep dive. How do you actually send these fragile quantum bits, these qubits, over long distances?
That's the billion-dollar question. And the answer seems to be this device, the quantum repeater.
Before we get to that, we have to appreciate the problem it's solving. It comes down to something called the no-cloning theorem.
Which means you can't copy a quantum state.
You can't. And you can't amplify it like a normal signal either. Any attempt to measure or duplicate it, it just destroys it.
Which is great for security because you know instantly if someone's listening.
A perfect built-in alarm.
But it's terrible for sending a photon down hundreds of kilometers of optical fiber. The signal just fades, doesn't it?
It does. The loss is exponential. After just 100 kilometers, maybe only one photon in 100 makes it. You can't build a global network on that.
Okay, so solving that kind of engineering problem requires some seriously sophisticated thinking. The level of complexity here is just incredible. This deep dive is brought to you by Embersilk. If you're tackling complex challenges in AI training, automation, or software integration, or even just trying to figure out where agent technology could make an impact for your business, check them out at embersilk.com.
So how do we get around that signal loss? That's where the quantum repeater comes in. It's a completely different approach.
It's not boosting the signal.
No, not at all.
Yeah.
Instead, it divides the long distance into shorter, more manageable segments. And then it uses quantum entanglement to kind of stitch them together.
So you're creating a chain of entangled particles.
Exactly. And then it uses a process called entanglement swapping to essentially teleport the quantum information from the end of one segment to the start of the next one.
Wait, teleport? You mean you're actually moving the quantum state without physically sending the particle across?
That's it. You're renewing the state before it's lost, all without violating the no-cloning theorem. It's brilliant, really.
Okay, so let's talk about the breakthrough. Just this month, November 2025, a team from Stuttgart, Saarbrücken, and Dresden.
A huge milestone.
They successfully teleported the polarization state of a photon from one quantum dot to a photon from a second, completely separate quantum dot.
And that separation is the key. That was the hard part.
Why was it so difficult?
Because for this to work, for the entanglement to bridge those two independent nodes, the photons they create have to be perfectly indistinguishable.
Like identical twins.
More than that.
Yeah.
They need the exact same color, the same timing, the same shape. If they're even slightly different, the link just collapses. It required some really advanced semiconductor light sources and quantum frequency converters just to tune them to be perfect matches.
And how did they do on the practical side? The lab demo was over 10 meters of fiber, but they'd done other tests, right?
They had, and this is the amazing part. Previous work from the same group showed the entanglement from these quantum dots survived, being sent through 36 kilometers of fiber, laid under the city of Stuttgart.
Wow. So this isn't just a fragile lab experiment. It works in the real world with all the noise and vibrations.
It does, and the success rate for the teleportation is already over 70%. They're working on fabrication techniques to push that even higher.
So when you connect this progress to the big picture, what does this unlock?
It's foundational. The ability to reliably link distant separate nodes is the first step toward building true multi-qubit fault-tolerant networks.
Which means things like distributed quantum computing.
Yes, and even entirely new scientific instruments. Imagine linking optical telescopes thousands of kilometers apart to get images of planets with a sharpness we can't even dream of today. Well, it's an incredible demonstration of what we can achieve. It just shows this amazing human capacity for solving these incredibly complex problems.
That is a truly inspiring vision for the future. If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.